Hi, my name is Andy Jaros, and I am the VP of Sales of Marketing and Solutions Architecture for Flex Logix. Today, what we're going to talk about is on-chip FPGA and using it as the other compute resource. When system companies are really looking at specifying their next generation products, the typical question and discussion always comes up: what should the processor subsystem look like? Do you take your existing subsystem and add more processors to it, maybe more or upgrading your processor to the next architectural level and higher performance? Or do you add more processing capabilities such as a DSP or GPU to give you more variability? One compute resource that rarely, if ever, gets considered is on FPGA, also known as embedded FPGA or eFPGA. And that's understandable for two reasons. FPGAs that can be integrated onto a chip is a relatively new IP, so there have not been a lot of usage of that type of technology in the past. And when people think about FPGAs, they don't necessarily think of it as a compute resource. Before coming to Flex Logix, I thought of FPGAs pretty much like everyone else. It's an alternative to a custom ASIC for low volume applications that don't have stringent power requirements. It's basically a blank sheet that you can program any circuitry into it. While embedded FPGA functionality is essentially the same as FPGA chips, embedded FPGAs are actually more powerful because they can go anywhere in an SoC and can execute certain functions better than an embedded processor. For the next several slides, we'll go through a number of use cases, and then we'll wrap up with the benefits of embedded FPGA. First case we'll take a look at is a simple case for reconfigurable I/O. And for this one, let's take a look at a camera SoC as an example. Camera manufacturers are coming out with all kinds of new functionality and capabilities. And usually what it leads to is a kind of a different interface when they add that kind of capability to the camera itself. And that poses a problem for the chip manufacturer because now the chip that they have developed for the camera market may need to be changed, updated, or taped out again to support new interfaces or modified interfaces. And this is where embedded FPGA can come in handy because you can use the I/O to have some flexibility in your interface. So if an application or a new camera comes online or a camera manufacturer has a new specification, you can actually modify the signals that get routed to the GPIO of the camera SoC and be able to support any new and upcoming requirements that the camera manufacturer may have. Another use case could be as a coprocessor. And here we'll start off with a simple example of filtering. We ran a benchmark comparing the energy consumption required to run several filter operations with a small embedded FPGA is compared to an embedded CPU with DSP instructions. And what we found is that the embedded CPU took 50 to 600% more energy to execute that particular filter application, despite the embedded FPGA being significantly larger. And this was primarily because the design in the FPGA was able to execute the function in orders of magnitude fewer cycles than the CPU and didn't have delays associated with reading and writing to memory. We have an application note available, which can be found on our website if you're interested in learning more. Related to filtering our sensors, it seems like more and more devices these days are adding more and more sensors and generating more and more data. Filtering out the unneeded data is being pushed to the edge to lower the processing load on the main processor and lower overall system power. Edge processing choices tend to be small embedded CPUs or state machines. A small simple state machine can be programmed into the embedded FPGA to target a sensor for a specific application. Yet the sensor can be programmed with a different state machine for entirely different applications and not conceived of when the sensor was developed, thereby extending the market for that sensor. The issue with dedicating a particular state machine in with the sensor is that you don't have the ability to change that state machine once the use case changes, or new applications may come up for that particular sensor. Additionally, by using binary neural networks, you can actually do some AI processing on relatively few number of LUTs with a small amount of embedded FPGA. Again, kind of extending the processing capability above a reprogrammable state machine to actually doing some AI functionality in sorting at the sensor level itself. Another example is motor controls. Factories are installing industrial robots, automated guided vehicles, collaborative robots, and smart sensor assemblies. These real-time applications need designs to achieve high performance, smaller footprint, and energy efficiency. Hardware can reduce the software latency by 100 or even 1,000 times, thereby improving performance. And implementing embedded FPGA meets all the requirements of smaller footprint and energy efficiency, with the extra benefit of providing the flexibility to update it in the factory. These apply to applications that require hardware performance and need the flexibility in their usage model and the ability to reprogram. One example of somebody actually using embedded FPGA in a microcontroller or a small embedded device is Sandia National Labs, who developed a chip. They have dual ARM7 processors, and they use the embedded FPGA for internal IP connections and implementing custom hardware blocks. With some fixed blocks, the FPGA can be reconfigured with AHB, SPIs, JTAG, or be used for hardware-based CRC or acceleration of software-based encryption. For all these use cases, we can see that the embedded FPGA is a powerful engine that's supporting the embedded processor on chip. Moving up the performance requirements is using embedded FPGA for packet processing. Many NIC applications require looking at specific bits in a wide data packet and performing some type of calculation prior to sending the packet on to the next stage in the pipeline. The specific bits that need to be modified change from application to application, necessitating programmability. There are several ways to address the programmability. One is use embedded processors. However, they inherently induce latency due to the dependencies on local cache memory with direct impacts to throughput. You can use dedicated state machines like we talked about earlier. They give better performance, but are inflexible once committed to silicon. An embedded FPGA is an ideal solution because they provide near ASIC performance, yet have full reprogrammability. An added bonus is that the designers do not need to over-design their state machine to anticipate every possible future use case. They simply program in a new state machine. Other networking uses for embedded FPGA include offloads for virtual switching, block storage, encryption, decryption, offload engines, IPsec, machine learning, deep packet inspection, video transcoding, and analytics. And then, of course, there's the whole concept of accelerators. It's well documented that using dedicated hardware accelerators is how chip architects are driving performance increases due to the flattening of Moore's law. In this case, the embedded FPGA is used as a sidecar to house the accelerator and provide near basic performance and full programmability once again. And one of the other main benefits is a reduction in latency. And that kind of leads to in the benefits of integrating the embedded FPGA to on-chip. And wherever it is possible to do any type of integration, the system that the chip is going into will save on power and reduce the number of redundant circuitries on chip. In the case of FPGA integration, the amount of SerDes gets reduced because you no longer need the SerDes that are on the FPGA because they already reside on the ASIC that's being developed. Performance is increased. Reduction in system cost is achieved through reducing testing time, fewer manufacturing failures, and less products to inventory, providing more value to the semiconductor customers. The other advantage of integrating the FPGA is the ability to actually choose the size of FPGA fabric that you want. FPGAs often come with features and interfaces that already exist in the ASIC, like we talked about in SerDes in the last slide. but those circuits tend to be on the ASIC as well. Embedded FPGA allows you to add in just the FPGA fabric and how much of that fabric that you want. What we're showing here is our graphical user interface that allows you to be able to scale and size the embedded FPGA, the amount of FPGA fabric that you might need for any given market application. And most people think that FPGAs are high-powered and very, very expensive, which they are. But embedded FPGAs shouldn't suffer the same reputation as FPGAs. They can actually be very, very low power, as been demonstrated by Laz's ICE40 and Renes's recently announced Ford's FPGA. That they are proof points that FPGA technology can be used for very low power applications, such as battery-powered remote IoT applications. And this is true for embedded FPGA intellectual property as well. One other useful application that we're seeing for embedded FPGA is keeping designs confidential through obfuscation. By programming the embedded FPGA after manufacturing in a secure location, whether it's a customer's manufacturing plant, or as a download in a system, those proprietary algorithms are kept secret. So nobody sees them except the people who are actually doing the programming of the chip itself. And then depending upon the applications, such as encryption, FPGA may help ease manage export control and ITAR requirements as well. One of the more recent trends that's taking place in the market is companies are exploring a chiplet approach to increasing process power and flexibility to support customized semiconductor solutions without having to take out an ASIC for each end customer. Using embedded FPGA to make an FPGA chiplet provides the extension of this chiplet ecosystem and avoids the reliance on securing known good die from FPGA companies and puts you in control of the supply chain in developing your own chips, and managing your chiplet ecosystem. There are lots of benefits for integrating an embedded FPGA. Programmability like a CPU or a DSP, but the parallel processing power and speed similar to hardware. And like a CPU, its reprogrammability anytime saves mask respins and saves lots of money. And if you don't want people to know what's in your FPGA, you can make it secure by encrypting the bit stream or hiding your circuits within the embedded FPGA itself. Yet you also save power and provide future flexibility and the ability to upgrade your system down, upgrade your chip in the future. This saves total system power, and saving total system power is one of the important benefits. And Flex Logix provides the embedded FPGA technology with a very unique solution. The unique solution is based on our interconnect. And really kind of the net effect of our interconnect is it gets us the same density as meaning the same number of LUTs per square millimeter as a full custom design from Xilinx or Intel. So if you're going to integrate FPGA, you want the highest density of LUTs per square millimeter that you can get. And the other benefit of our interconnect is the ability to achieve high utilization. So we tend to get close to 90% utilization of the available LUTs as compared to 70% of off-the-shelf FPGAs. So if you're going to dedicate a certain number of square millimeters of your ASIC to FPGA, you want to be able to use all the logic, as much of that logic capacity as possible. And with our interconnect, it allows us a design methodology that makes us extremely integratable. So the shortest time that we've delivered our product to a customer taping out a chip with embedded FPGA has been 2.5 months. The embedded FPGA business is growing. We're up to 23 chips that have been working in silicon. We have 10 customer chips in design and many more that are in the pipeline. We have 16 licensees so far and multiple customers doing multiple chips, having having very positive experience with the first chip. They are believers in the IP and that technology and moving it forward in their product roadmaps. We also provide the most support on available process nodes from 180 nanometers down to 7, and we'll soon be working on 5 nanometer. We have multiple products, and we can scale our capacity from 1,000 to 2 million bucks. So I want to thank you for your time and learning a little bit more about using embedded FPGA as or thinking about using embedded FPGA as an alternative to adding in another processor to your system. And if you have any questions, feel free to contact me at andy@flex-logix.com.